Welcome to lesson 29 on power system analysis. In this lesson, we will continue with unbalanced fault analysis. The symmetrical faults that we were considering in the previous lectures were the short circuits. In this lecture, we will consider the open circuit faults. So, here we will start with an introduction, then we will discuss one line open fault and then two line open fault, and after that we will discuss a little about fault analysis for large power systems. Well, on completion of this lesson, you should be able to develop sequence network connections for open circuit faults, and you should be able to explain the objectives of fault analysis for large power systems. As we discussed in the previous lesson, there are different kinds of faults which occur in power system, such as line to ground fault or line to ground faults and line to line faults. These are asymmetrical faults. Similarly, three phase to ground faults, there is a symmetrical fault. All these faults are basically short circuit faults, whereas we have other types of faults which are basically open circuit faults, like a single phase open, that is one line gets open or two line gets open. In both these cases, the fault again is an asymmetrical fault, because the voltage and currents in all the three phases are not balanced or symmetrical. Now, when we one question which comes to mind is, we can understand studying the short circuit faults, because in case of short circuit, heavy currents are going to flow in the circuit, and we need to protect our equipment from damage because of this heavy current. What happens in case of open circuit faults? Well, open circuit faults in most of the cases will lead to over voltages, and that is why we need to study them, because these over voltages can sometimes cause insulation failure and thereby resulting in a short circuit. So, we need to study these open circuit faults also to make sure that our system design for insulation can take care of the over voltages caused by the open circuit faults. Now, how do we simulate these open circuit faults? Well, if you see here, we have phase A, B and C. In these three phases, we have impedances ZA, ZB and ZC. Now, we are considering a fault occurs between these points F and F dash on two sides of these impedances. These impedances can be the line impedances themselves, and the point F and F dash can be the two bus bars, or it can be any 2 points where the line gets broken or there is an open circuit in any equipment. So, here as we have shown, phase A is carrying current IA, phase B is carrying current IB and phase C is carrying current IC. The impedances ZA, ZB, ZC are not same, and thereby the currents will also be not same. That means we have a symmetrical operating condition here. Now, these, if we assume ZA to be infinite or very large, we can simulate a fault which is an open circuit on phase A. Similarly, ZB or ZC can be made infinite or very large, which will simulate a fault of open circuit of phase B and C. So, in this way, if we, by making these impedance values very large or infinite, we can simulate open circuit faults on this system, and that is why these open conductor faults or open circuit faults are sometimes called series faults. That means what we are doing is we are introducing a large impedance in series with the circuit, and for simulating these faults. Now, what happens in case of these series faults or open conductor faults? Let us see how do we define the currents and voltages in case of open circuit faults or open conductor faults. The currents are in phase variables IA, IB and IC, and the voltage across the faulted portion, if you see this across this portion, that is between F and F dash of this system, we see the voltages as VAA dash, VBB dash and VCC dash as seen here, that is voltage between A and A dash, B and B dash and C dash and so on. We can convert this into symmetrical component variables, and we can write this as IS, which is symmetrical component for the currents. So, we have IA1, IA2 and IA0 as the symmetrical component currents for this system, and Vs is equal to VAA dash 1, VAA dash 2 and VA dash 0. So, this is the transformed currents and voltages in the sequence network. Now, for this system, compared to the short circuits that we have done, there is some difference. The difference that we find here is that here we have 2 points A and A dash for the faults in all the phases A dash, B dash and C dash. That is, we have 2 points F and F dash in the system which involve the fault, whereas in case of short circuit faults we had seen we had only 1 point F where the fault had occurred. So, in trying to obtain the sequence network for this, we will also have these 2 points F and F dash. So, this is the reference, this is the positive sequence network, this is the reference, and we have F and F dash as the 2 points of indicating the fault, and the voltage between these 2 points is VAA dash 1, which is the positive sequence voltage, and the current flowing is IA1 and entering is IA dash 1. In fact, as we will see, these currents will be equal. Similarly, the negative sequence, we have the reference here and we have 2 points F and F dash, where the current IA2 is coming out from F and IA dash 2 is entering F dash. Now, in case of negative sequence network, VAA dash 2 is the voltage between F and F dash. Similarly, we have the 0 sequence network, reference here 2 points F and F dash, IA 0 coming out from F, IA dash 0 entering F dash, and VAA dash 0 is the voltage between F and F dash for this network. Now, what we need to do is we need to find out the connection between the 3 sequence network for different types of fault. But here what we find is the situation is somewhat more complex than what we had seen in case of a short circuit. Here we have 2 points F and F dash, that means we have to get the Thevenin's equivalent between F dash and reference as well as between F and reference. That means we have to think of Thevenin's equivalent in terms of 2 port network, because here we have a 2 port network between F dash and the reference and F and reference for each of the sequence network. So, we need to take care of this using the theory from 2 port network. So, here I have shown this as a 2 port network where we have IA flowing in on the input side. So, this side we have IA flowing in and VA is the voltage, and this side IA dash going out and VA dash is the voltage. Now, we can write down the voltage and current relationship for this 2 port network as VA dash is equal to ZAA dash ZA dash A and Z A dash into I A dash. Now, these impedances are basically called the open circuit impedance for this network. That is, you will get this impedance by keeping this open and supplying current here. If say you supply 1 ampere current here and you measure the voltage here, then you will get ZAA dash, sorry, ZAA. Similarly, if you supply a current here keeping this open, if you measure the voltage here, you will get ZAA dash. And so, in this way we can find out these impedances, and here we have written this VSA and VSA dash. Now, these are basically the voltages or the voltage sources which are connected in this system. So, on this side as well as this side, so they are taken care by means of this VSA and VSA dash. Therefore, in short, we can write this relationship as V is equal to ZI plus Vs. So, how do we use this two-port network relationship in case of our sequence networks? Now, as we have seen that we have in this case a system where we have IA1 coming out and IA dash 1 going in. Now, in case there is no crossover of wires, that means the phases are not coming in contact with the other phase, then we will the external conditions of the system will see that the value of IA1 and IA dash 1 will be same. That is, the current flowing out of the positive sequence network will be same as the flowing into the positive sequence network at this point F dash. So, network external connections impose the condition that minus I012 is equal to I012 dash. That means, the current sequence currents flowing out of the F point are same as that flowing into the F point. That is, minus IA1 is equal to this is equal to IA dash 1 minus IA2 is equal to IA dash 2. I am sorry, these dashes should come here, and I minus IA0 is equal to IA0 IA dash 0. Current entering the node is considered positive. So, current coming out, that is from the terminal F, have been put as negative here. Therefore, for positive sequence network we can write VA1 and VA dash 1 is equal to ZAA1, ZAA dash 1, ZA dash A1 and ZA dash A dash 1. These are the open circuit impedances for this two-port network that we have, and is into minus IA1, because we have put this minus IA1 because we are taking current entering as positive. So, minus IA1 and plus IA1 because IA dash 1 is basically equal to IA1. So, here we have this minus IA1 and IA1 here, because the magnitudes are same for both, as we have said that the next network external connections impose this condition when there is no crossover of the phase. So, plus VSA1 and VSA dash 1. These are the internal voltage sources in the two sides of the network. So, this we can write again as VA1 VA dash 1 is equal to this we have taken on this side into this, we have simplified this, then we get this ZAA1 minus ZAA dash 1 into IA1 and minus ZA dash A dash 1 IA1 plus ZA dash 1 into IA1. So, after simplifying, if we write this ZAA1 into minus IA1, ZA dash 1 into IA1. So, minus has been taken here. So, this minus comes here. Now, this is ZA dash A1 this is minus here, and sorry, this minus is missing here. So, minus we have taken here. So, this is positive because Z A dash 1 into I A 1 is here. So, Z A dash 1 into I A 1. Now, since it is positive, this is minus we have taken here. So, minus is here, and this will be minus here. So, this becomes plus and then this becomes minus. So, it is finally minus Z A dash 1 into I A 1. So, this is the relationship that we get, which we can write in circuit form like this, where we have V s A 1 is the voltage of the internal voltages in the system. So, that is put here, and we have the impedance Z A 1 minus Z A dash 1 as the series impedance connected to this source, and I A 1 is the current coming out at this point F 1. And similarly, for the other side, on the F dash side, we have V s A 1 dash V s A dash 1, that is the internal voltage on that side, and the impedance is Z A dash 1 minus Z A dash 1. This minus sign is missing here. So, and the current is entering this node as F 1 dash, and the voltage across this is V A dash 1, and the voltage here is V A 1. That is, if we remember this, we are saying this voltage is V A 1 and this is V A dash 1. So, between reference and point F and F dash. So, here this is what we get. I am sorry. So, this is, and the V f, the voltage at the fault point, which is equal to your V A dash 1 minus V A 1 minus V A dash 1 is the voltage which is coming between these 2 points, that is V A dash. So, for the positive sequence, and this is the voltage or the open circuit voltage across the fault point, which we get as the Thevenin's equivalent voltage which will be coming. So, this is the uncoupled positive sequence network between the fault points F and F dash. Here we can write the, if we say that the total current which flows, or the positive sequence current which flows through the network encounters positive sequence impedance of the network, then the positive sequence impedance Z 1 can be seen as this impedance and this impedance in series, because this is I A 1 flowing, and through this flowing through the other parts of the network comes out like this. So, the current I A 1 is seeing this impedance and this impedance in series. So, we get Z 1 as Z A 1 minus Z A dash 1 plus, that is this impedance, plus this impedance, this is Z A dash 1 minus Z A dash 1. So, this is what we will get as the total positive sequence impedance for this network. Similarly, we can get the uncoupled negative sequence network between point F and F dash for the system. In the same way, the impedance in this case will be Z A 2 minus Z A dash 2 and Z A dash 2 minus Z A dash 2. The minus should be here, and the points, these are F 2 and F 2 dash, and the current flowing here is I A 2, and the current, same current after flowing through other parts of the circuit will be entering this point F 2 dash as I A 2 dash, which is same as I A 2. This will be entering here. Now, again, since we have said that negative sequence impedance is the impedance offered by the network to current, negative sequence current flowing into the network. So, this is the negative sequence current flowing into the network. So, the impedance offered by the network to this current will be this impedance plus this impedance. So, we can write Z 2 is equal to Z A 2 minus Z A dash 2 plus Z A dash 2 minus Z A dash 2. So, this is the total negative sequence impedance seen by the current for the network, or this is the negative sequence impedance of the network for this system. Similarly, we can get the 0 sequence network for this F0 and F0 dash points. So, here again the impedance is Z A 0 minus Z A dash 0, and this impedance is Z A dash 0 minus Z A dash 0, and we see that negative and 0 sequence network do not have any voltage sources associated with them, which is what we had seen earlier also. So, here also there will be no such sources. So, uncoupled 0 sequence network between fault points F and F dash is like this, and the impedance offered to 0 sequence current by this network will be equal to sum of these two impedances, that is Z0 is equal to Z A 0 minus Z A dash 0 plus Z A dash 0 minus Z A dash 0. So, this is the total impedance which will this network will see. Now, for simulating the open conductor faults, since we are simulating only one conductor or two conductor open faults, in case of 3 conductor open faults we do not need any analysis as such, because in that case there will be no current flowing through the system again will be symmetrical open circuit system. So, since we are simulating only one phase open or two phase open, so what we can do is we can use Z A as infinity if we are assuming or we are simulating phase single conductor open, that is one phase open. So, phase A open with Z A infinity, or when we are simulating two phases open, then we can assume Z B to be infinity. So, we do not need to create this for separate Z A, Z B, Z C. In fact, we can assume for simulation Z B and Z C are equal and Z A is separate in phase A. So, when we want to simulate one conductor open, Z A can be made infinite, where Z B will be finite. If we want two conductor open, Z B will be infinite and Z A will be finite. So, this way we can simulate this. Now, let us see with this situation what happens. So, again we can write down the voltage equation for the system as VAA dash, VBB dash and VCC dash in phase components. So, this will be equal to VA minus VA dash, VB minus VB dash, VC minus VC dash, which will be equal to ZA into IA, ZB into IB and ZC into IC. That is, if we see here, VA minus VA dash will be nothing but IA into ZA. Here we are assuming there are no mutual couplings between these phase impedances. So, in this way we can write this relationship in this simple form, that is, we can write VABC minus VA dash B dash C dash is equal to ZABC into IABC. Now, this can also be written in terms of sequence component as VAA dash 012 is equal to V 012 minus V dash 012, that is positive sequence voltages at point F and positive sequence voltages at point F dash. So, subtraction of these two will be equal to Z012 into I012, where this Z012 as we have seen earlier will be nothing but equal to A inverse Z ABC into A, where A is the symmetrical component transformation matrix. So, Z012 is equal to A inverse Z ABC into A. This is what we will write for this to get this Z012, and then we find that V012 minus V dash 012 is equal to Z012 into I012. That means the phase quantities are now converted into sequence quantities. Now, if we do this, then we find that Z012 is equal to 1 by 3 into ZA plus 2 ZB, ZA minus ZB, ZA minus ZB. So, that is what we are finding, that in this case the diagonal elements are equal to ZA plus 2 ZB and all the off diagonal elements are equal to ZA minus ZB. That this is a symmetric matrix with all the diagonal elements having the same value and all the off diagonal elements having the same value. The diagonal elements are ZA plus 2 ZB, whereas the off diagonal elements are ZA minus ZB. And of course, this 1 by 3 comes because of the transformation that we have. So, in this case we can write this as VAA dash 0 is equal to VA 0 minus VA dash 0. Similarly, for positive sequence, VAA dash 1 is equal to VA 1 minus VA dash 1, VA 2 is equal to VA 2 minus VA dash 2. This is equal to this Z012 into I012, that is IA0, IA1, IA2. So, this is what we will get, and if we use this relationship, that is subtracting row 2 from row 1, that is from this row 2, if we subtract, this is ZB ZA minus ZB into IA0, ZA plus 2 ZB into IA1 plus ZA minus ZB into IA2. This we subtract from row 1, that is ZA plus 2 ZB into IA0 plus ZA minus ZB into IA1 plus ZA minus ZB into IA2. Then, and arranging this, we will get VAA dash 0 minus VAA dash 1 is equal to ZB into IA0 minus IA1. That is, if we do this subtraction of the row 2 from row 1, this is what we are going to get, and this we can write as ZAA dash 0 minus ZB into IA0. This term we are taking on this side. Now, this term we are taking on right hand side. So, this becomes positive. So, VAA dash 1 minus ZB into IA1. So, this is what we will get by subtracting row 2 from row 1. Now, similarly, subtracting row 3 from row 2, we will get VAA dash 1 minus VAA dash 2 is equal to ZB into IA1 minus IA2, which will give us VAA dash 1 minus ZB into IA1. ZB into IA1 we are taking on this side, so it becomes negative. This VAA dash 2 we are taking on this side, so it becomes positive, minus IA2 into ZB. So, this is minus ZB into IA2. So, these two relationships that we are getting here like this. Now, from this what we are seeing, VAA dash 0 minus ZB into IA0 is equal to VAA dash 1 minus ZB into IA1 is equal to VAA dash 2 minus ZB into IA2. That is, if we see here, this term VAA dash 1 minus ZB into IA is here also. So, which means this term is equal to this term is equal to this term. So, this is what we are writing here, that is VAA dash 0 minus ZB into IA0 is equal to VAA dash 1 minus ZB into IA1 is equal to VAA dash 2 minus ZB into IA2. Now, adding row 1 and row 2, what we will get? That is, again, if we go here and add row 1 and row 2, what we are going to get? We will get VAA dash 0 plus VAA dash 1 is equal to 1 by 3 into 2 ZA plus ZB into IA0 plus IA1 plus 2 by 3 ZA minus ZB into IA2. Now, substituting for VAA dash 0 and simplifying, that is, from here we can substitute the value by putting this side on this side, and simplifying we will get VAA dash 1 is minus ZB into IA1 is equal to 1 by 3 Z A minus Z B into I A 0 plus I A 1 plus I A 2. That is, what we have done is substituting the value of this here from this one, and then we will get this V A A dash 1 minus Z B into I A 1 is equal to this term. So, from above two equations we get the sequence network connections as. Now, what does this say? This is saying V A dash 0 minus Z B into I A 0 is equal to V A dash 1 minus Z B into I A 1 and V A dash 2 minus Z B into I A 2, means this Z B is connected in series with this negative sequence network, positive sequence network and 0 sequence network. And we also have from this that V A dash 1 minus Z B into I A 1 is equal to 1 by 3 Z B minus Z A minus Z B into this, that is, sum of all these three currents will also flow through this impedance. So, if we use these to this equation and this equation, then we will get a connection of the circuit like this, that is V A 0 in which through Z B is connected in series with this. So, I A dash 0 is flowing into this. So, this is V A dash 0 minus Z B into I A 0 is the voltage across these 2 points. Similarly, V A dash 1 minus Z B into I A 1 is the voltage which is coming across these 2 points. Similarly, V A dash 2 minus Z B into I A 2 dash I A 2 is giving us voltage between these 2 points. So, that is why, and these are equal. So, we have connected them. We also see that the current, this current is flowing, this is I A 2, I A 1 and I A 0 is flowing through this impedance 1 by 3 Z A minus Z B, and this is equal to this voltage which is same as this voltage. So, this is the circuit that we get in case of these system where we have a Z A in phase A and Z B and Z B in phase C, B and C respectively. So, this is the sequence network connection that we are getting. Now, if we want to simulate one conductor out or a single phase open, then we can do that very easily by substituting Z A is equal to infinity and Z B as finite. But before we do that, we need to compute the value of Z 0, Z 1 and Z 2 for this circuit. So, if we see here what is the current which is flowing through, that is I A 1 is flowing through which circuit, then we find this Z B is there and the circuit that we had seen for this positive sequence network, that will be there. So, Z B is in series with that, and similarly for this we will find for Z 2 will be in series with this Z B and Z 0 in series with this, and of course 1 by 3 Z A minus Z B is in parallel with these. So, if we do this circuit reduction, then we have Z 0 is equal to Z A 0 minus Z A dash 0 plus this. So, this we have seen is equal to this, Z 1 we have seen is equal to this, Z 2 we have seen is equal to this, that is simply adding this, this is what we get. And V F is equal to V S A 1 minus V S A dash 1, this is equal to V A dash 1. This is what we had seen in this circuit earlier. V F is equal to V S A 1 minus V S A dash 1. This is what we have seen, this is equal to V F. So, this is what we have. So, V F is this, we have Z 1, Z 2, Z 0 that we had calculated earlier. So, these can be substituted here. So, we have the complete circuit now like this, V f Z1 in series with that, and we have now this current I1 flowing through this, and then we have this ZB here, and this is the point where we have this is the point, these 2 points of the circuit. And then again if we take 0 sequence or negative sequence, then we have Z0 and ZB in series. So, we have Z0 and ZB in series, similarly Z2 and ZB in series, and here I2 is flowing, here I0 is flowing, and here we have I0 plus I1 plus I2 flowing. So, this is I1 flowing, this is I2 flowing, this is I0 flowing through this circuit, and I1 plus I2 plus I0 flowing through this circuit like this. So, this is the complete circuit which defines the sequence network connection for the system where we have an impedance Z A in phase A and impedance ZB in phase B as well as phase C. Now, as we said, we can calculate the positive, negative and 0 sequence current for this circuit. So, we can do that. I1 will be equal to V f by ZT, that is, if we see this circuit, V f is the voltage and this is the total impedance of this circuit is ZT, and we need to find out what is ZT. So, ZT will be equal to Z1 plus ZB, that is again if we see this is Z1 in series and ZB in series in which I1 is flowing, and this rest of the circuit is again can be reduced into one impedance connected between these 2 points. So, if we do that, that is these 3 impedance arms are in parallel. So, we need to find out an equivalent for these 3. So, that is Z, and we can write this Z is equal to Z0 plus ZB into Z2 plus ZB into ZA minus ZB divided by ZA minus ZB into Z0 plus ZB plus ZA minus ZB into Z2 plus ZB plus 3 times Z0 plus ZB into Z2 plus ZB. That is what we have done is reduce these 3 arms into a single impedance Z. Then we have Z1 plus this Z plus ZB, that is equal to ZT. So, if we do that, then we have this I1 computed like this, I2 is a part of the current which is flowing in that. So, this can be written as minus I1 Z divided by Z2 plus ZB, and I0 will be minus I1 Z divided by Z0 plus ZB. So, since I1 is flowing and total impedance as we had seen is this impedance is Z, a part of this goes through this and rest will go through this. So, we have this ratio coming into picture. So, Z by Z2 plus ZB and Z by Z0 plus ZB for I0, and I2 we have Z by Z2 plus ZB part of the current I1 will be flowing. So, this is how we can calculate the positive, negative and 0 sequence current flowing into this system. Now, we want to simulate one line open or a single phase open fault. Again here as we have seen, we have this fault created between 2 points F and F dash. Now, in this case what we have, ZA is infinite if we see the previous system, and ZB is finite. So, substituting ZB as finite. So, these 2 lines are connected and we have a finite impedance here, and there is an infinite impedance here because it is open here. So, with this if we see, then what happens if we go back to this circuit, what we find substituting ZA is equal to infinite means this becomes infinite. So, this is an open circuit, rest of the circuit we do not have ZA. So, rest of the circuit remains as it is. So, this is what we get in this case. that is, this is the system that we have, where we have Z A as, here we had Z A minus Z 1 by 3 Z A minus Z B, that part is now infinite. So, it is open. So, when we reduce this circuit, we reduce it to this form, that part here 1 by 3 Z A minus Z B is no longer connected in parallel, that is open. So, this is the total circuit that we have, and we can calculate I 1, I 2 and I 0 for this circuit. So, we get I 1 is equal to V f by Z t, and Z t in this case will be equal to Z 1 plus Z b plus Z, that is again Z 1 plus Z b plus Z, which is parallel of these two arms. So, we can do this. Z is equal to Z 0 plus Z b into Z 2 plus Z b divided by Z 0 plus Z 2 plus 2 Z b, and once we know I 1, we can calculate I 2 is equal to minus I 1 into Z by Z 2 plus Z b, and I 0 will be minus I 1 Z divided by Z 0 plus Z b, and so this way we can compute all the three currents, sequence currents, and then we can convert them to to phase values, and we can calculate the voltages in the same way. Now, for a two line open fault, that is phase B and C are open, this can be simulated by putting Z b is equal to infinite and Z a as finite. That means I b and I c in this case is equal to 0. Now, if that is the situation, then we can write this I 0, I 1, I 2 is equal to 1 by 3 into, this is the transformation matrix that we have, A inverse, and this is I a, I b and I c. Now, I b and I c are 0. So, what we get? We get I 0 is equal to 1 by 3 into I a, I 1 is equal to 1 by 3 into I a, I 2 is equal to 1 by 3 into I a. These two are 0. So, we get 1 by 3 I a, I a, I a. So, what does this say? This says that the three sequence currents are equal, which means the three sequence networks are connected in series. So, this is what we will get here. This is the 0 sequence network. Z a is connected in series like this to F dash, then from F again Z a is connected to F here, and then F dash here, and then from F Z a is connected and it comes to this point. So, the three networks are in series as such, with Z a, Z a and Z a connected here. Therefore, we get I 1 is equal to I 2 is equal to I 0. This is equal to V f divided by Z 1 plus Z 2 plus Z 0 plus 3 Z a. So, in this case, this is how we calculate the currents, sequence currents. Once we know the sequence currents, we can calculate the sequence voltages at any point, and converting them, we will find out the phase voltages at fault point or any other point in the system. So, this is how we can solve for open circuit faults using the sequence network connections. So, after this, we will summarize whatever we have done till now in case of faulted system analysis. How do we carry it out? So, what we do is we will write down the algorithm for analysis of faulted power system. What we do first is obtain the pre-fault steady state solution of the system, that is the pre-fault conditions. We find out if we don't know or don't want to calculate these values, or we have unloaded system, that is we have assumed that the system is initially unloaded, then of course, we know the voltages are 1 and the currents are 0. So, but if we want to take into account the loaded system condition at which the fault has occurred, then we can of course, do a load flow study and find out the voltage and currents in various parts of the system. So, we know the pre-fault steady state solution of the system by doing a load flow study. Now, after this, assemble the system models consisting of three separate sequence networks. That is, we create the 3 sequence networks, positive, negative and 0 sequence networks with their appropriate impedances, which means if we are interested in the fault current immediately after the fault has occurred, then we take the subtransient impedances. If we are interested in finding out the current after some time, that is when the breaker opens the circuit, maybe after 2 cycles or 5 cycles like that, then we may substitute transient impedances instead of the subtransient impedances. And if we are interested in sustained fault current, that is steady state fault current, then we need to substitute the steady state impedances, which is the synchronous impedances for the machines as such. So, appropriate impedance value and short all the voltage sources, that is, we have seen earlier that what we do is, for computing the fault currents using the Thevenin's theorem principle, what we are trying to do is find out the changes caused by introducing this fault. That is, we had seen that fault is acting as a structural change, that is inclusion of an impedance, fault impedance into the system, and this we can simulate by using Thevenin's theorem, that is by putting impedance at the fault point equal to this impedance in series with a voltage which is opposite to the open circuit voltage at the fault point. So, that is what we do in this case. So, for this purpose we have already eliminated all the voltage sources, that is all the generators are shorted and replaced by their appropriate impedances. Depending on the type and location of the fault, using the mathematical description of the same, make proper connections for the sequence network. That is, depending on the type of fault, if it is a single line to ground fault, then all the 3 impedance 3 sequence networks will be connected in series and so on. So, we need to do that. So, make the proper connections for the sequence network, then excite the positive sequence network at the fault point, is what I said. Excite the positive sequence network at the fault point by negative of the pre-fault voltage at that point in series with the fault impedance. This is what the Thevenin's theorem says, that we have reduced the network, passive network, by shorting all the voltage sources and replacing them by their appropriate impedances. Now, at the fault point we connect the voltage source of value which is equal to the negative of the open circuit voltage at that point, that we had found using the Thevenin's theorem, and in series this voltage is connected in series with the fault impedance at the fault point. So, between the fault point and the reference. So, this is how we do that. This, when we do this, will give us the currents and voltages caused by the introduction of the fault, that is the changes caused by this fault, and this can be added or superimposed on the pre-fault values, and therefore, we will get the final values. Solve the resulting network equations by means of Thevenin's theorem. Currents and voltages are found not only for the point of fault, but throughout the system. So, once we find these changes, what we do is we add it to the or superimpose on the pre-fault conditions that we have, and then we know the voltages and currents at various points in the system. So, this is the algorithm that we use for solving the faulted system, that is solving or analyzing the system under fault conditions. However, this does not work very well for large systems, because here we need to find out the reduced passive network at the fault point, which is very difficult to obtain for large systems. So, for small systems it is possible to reduce the sequence network into its Thevenin's equivalent at the fault point, but for large system it is extremely difficult to obtain such an equivalent. It is very complex to do that for a large system which has large number of lines and nodes in the system, that is bus bars in the system. For large systems, therefore, we need to develop a systematic and general procedure, that is some algorithm which is suitable for solution on computer. We need to do this for large systems, and we will see how we do it in detail in the next class. So, what we do before we start analyzing large system, we need to define the problem or state the problem. So, what we do is we say that the system under study has n buses, where n is maybe any number, a large number normally. It is initially operating in a symmetrical normal state, that is what we assume, that initial conditions are steady state conditions. All pre-fault bus voltages and power flows are assumed to be known, that is we have done the load flow study and we know the voltage and power flows. At a fault occurs at some bus q. So, any bus, it can be any bus q. Fault can be represented as a fault impedance matrix ZF. This again we will see how to do it. So, that is, if you see the system, we can define this is a n bus power system in which we have taken this bus q at which the fault has occurred. The fault impedance is ZF, and the ABC phase voltages are shown here for the bus q. So, with this we end today. In the next lesson we will talk about how to develop an algorithm for short circuit studies on large power systems. Thank you very much. Welcome to lesson 30 on power system analysis. In this lesson we will discuss fault analysis for large power system. We will start with an introduction, then we will discuss fault analysis for large power system using Y bus matrix, then we will talk about fault analysis using Z bus matrix, and then finally we will solve one example using Z bus matrix. Well, the instructional objective for this lesson is that on completion of this lesson you should be able to develop algorithm for fault analysis using Y bus method, explain the difficulties associated with fault analysis using Y bus method, develop an algorithm for fault analysis using Z bus method, and solve for fault current and bus voltages for a faulted power system using the Z bus method. Well, as we had discussed in lesson 29, that we can do symmetrical as well as asymmetrical fault analysis using Thevenin's theorem, but when we are trying to do it for a large system, trying to find out the Thevenin's equivalent of the network at the fault point is a very complex job. For small systems it is possible to reduce the sequence networks into its Thevenin's equivalent at the fault point. For large network it is extremely difficult to obtain such an equivalent, because you need reduction for a very large network with large number of voltage sources in the system. So, therefore, for these large systems we need some kind of a systematic method to solve this problem using a digital computer. So, we need to develop a systematic and general procedure which is suitable for solution on a computer. Now, how do we go about this? First, what we will do is we will define or we will state the problem for a large power system. So, what we will do is we will state a general problem in which we will say that system under study has n buses, where n is pretty large. It is initially operating in a symmetrical normal state, that is, before the fault has occurred, the system is working in a normal state, which is basically operating under a symmetrical loading condition. So, voltages and currents in the system are normal, they are not abnormal. So, load currents are there, the system voltages or the bus voltages at various places will be very near to their rated values. So, this is what we have written here, that although this algorithm looks straightforward, there are some difficulties associated with this. The algorithm involves inversion of n minus 1 into n minus 1 matrix y0 0. For finding out the circuit breaker ratings and relay settings, we require calculation of fault currents for faults at different buses. That is what we said, at various buses we need to compute, create the fault and find out the fault currents and the voltages. For each of these fault calculation, we will require inversion of y0 0 matrix, which will be different in each case. This is computationally very expensive, and this is the main reason why Y-bus based algorithm for fault analysis is not much preferred. Instead, we prefer the Z-bus based algorithm, and we will see how this Z-bus based algorithm works. Okay, so fault analysis using Z-bus method. Now again we have seen, using the Thevenin's theorem, the post fault bus voltages can be written as V bus F is equal to V bus 0 plus Z bus into I bus F. Okay. Now what is this I bus F? I bus F is basically the current injections at various points when the fault has occurred. Now, as we have seen, for Thevenin's equivalent, what we have written is that this delta V involves this delta I. This is because of the changes which have occurred, and in case of finding out the changes, we have already eliminated all generating sources. The only source which is available in the system is the voltage source at the fault point, and that is a current IF flowing from the bus towards the ground. So, if we see in terms of current injection at all the other buses except the qth bus is going to be 0, and at qth bus the current injection is nothing but the negative of the fault current, because fault current is flowing away from the bus to the ground, and since we write these equations in terms of current injections into the bus, therefore, we write this as minus IF.